Last time, when we started talking about sequences, we talked about how there are a few different ways of conveying what the sequence is. One thing we can do is list out the numbers in the sequence, but because these things are usually infinitely long, we can never list all of them. And while we can list enough to indicate what a pattern is, A, it might not be easy to spot a pattern if it's something a little bit more complicated, and B, we don't know for sure that that pattern is what's even intended. So often we prefer to use one of our other techniques, like a recursive definition or a closed form expression. So the recursive definitions typically say that, hey, our next term is going to be some formula that depends on previous term or terms. Whereas the closed form is just an expression that you plug in n and it spits out what the nth term should be. So what we're focusing on today is how to get from either a list or a pattern that we see in a list of numbers, or from a recursive definition to this closed form. So the goal today is to get some closed form expression where all you have to do is to say what the 12th term is just to plug in the number 12 into our formula. I should say that this isn't always doable just from the sequence. Even if you have a good portion of the sequence and you can recognize what you think the pattern is, we can't always necessarily find a closed form of it. It's often easiest to go back to sort of where the sequence came from and really ask more questions about, all right, what can we say about the actual situation, the actual thing that's generating this sequence, rather than just working off of a sequence. That said, there are a few different styles or types of sequences that if they follow certain patterns, then maybe we can figure out what the formula is, what the equation for this closed form expression should be. Okay, so the first few examples that I want to talk about all have to do with polynomials. So if we look at this sequence, 2, 4, 8, 10, 12, 14, etc., you might notice that these are the even numbers. So in other words, we already can sort of just spot that the nth term is 2n. We've even talked about this one before. But I want to point out a way that we might notice that. To get from the first term to the second term, we add 2. Second term to third term, we add 2. Third term to fourth term, etc. We are always just adding 2. So we're going to say that the sequence, this arithmetic sequence, is delta constant, because delta typically is referring to like a change in something. So in this case, this delta is the change between terms. The change is constant, therefore we say that the sequence is delta constant. With our second example, you might just spot off the bat that this is the squared sequence. Our an is just n squared. But I think we could imagine that if this was a slightly more complicated quadratic, maybe instead of n squared it was 3n squared minus 2n plus 1, then this might be a more difficult pattern to spot. So let's take a delta approach to what the sequence is doing. So the difference between the first two terms is 3. The difference between the second two terms is something different. So this is not a delta constant sequence. But if we keep going, we might notice some other pattern. The difference between third and fourth is 7. Then the next two is 9, 11, 13, etc. So now in this form, now you might spot the pattern, but let's just go one step further in case it's not obvious. The difference between the first and second terms of the differences between terms. So we're inceptioning our way into differences, but the difference between these two is 2, the difference between these two is 2, etc. So the sequence formed by the differences in our original sequence in itself has the property that it is delta constant. This new orange sequence is delta constant. So we say that this is delta 2 or delta squared constant, meaning that the second order is delta constant. With the last example, you might guess the pattern that's happening here. This example is the cubes. And if we repeat this process, if we ask ourselves, what is the difference between these first two terms? Well, we have to increase by 7, then we have to increase by 19. If we follow this pattern, you might guess where this is going. If we start with our original sequence and we calculate the differences between each of the terms, we get this orange sequence, which doesn't look like anything much to me, but if we repeat this process, we get to the blue one, which at least to me looks a little bit simpler. I might recognize this as an arithmetic sequence. If we go even further, we get to a constant sequence. So we say that this blue sequence is delta constant. By our previous example, orange is now delta squared constant. So to keep this consistent, we are saying that our black sequence is delta 3 constant. It's no coincidence that our cubic functions are giving us sequences that are delta cubed constant, whereas our squareds are giving us sequences that are delta squared constant. This ties a lot into derivatives of polynomials. So most of you have taken calculus. If we take the derivative of a cubic, we get a quadratic. And when we're doing this, how much is the difference type of calculation for our sequence? That's really similar to asking how quickly is something changing. A derivative is saying how quickly is a continuous function changing. But this is discrete math. We don't have continuous functions. We have discrete sequences. That said, a lot of these ideas are very similar. All right, so if a sequence is delta k constant, meaning if we go k levels deep, we'll end up with a sequence that is itself constant, then it can be represented by some k degree polynomial. And as it turns out, any degree k polynomial ends up being delta k constant. So this statement works in both directions. So if I wanted to use this in practice, say I was working with some discrete math homework question and I came across a sequence that looks like this. Well, in general, I would recommend trying to get a little bit more out of what the question was to begin with. But if all we had to work with was the sequence, there are still things that we can do. Namely, we can determine if this is delta k constant. So we can ask ourselves what the difference between these terms are. Well, those aren't constant, but maybe if we look at the difference between those, there we go. That shows that our original black sequence is delta squared constant, which means that our sequence looks like a quadratic. It looks like something of the form a times n squared plus b times n plus c. So we don't know what a, b, and c are. We're still going to determine that. But we do know that it follows this general format. So all that's left to do is to solve for these constants, a, b, and c. Well, we have 3 unknowns, and we actually have access to a lot of equations. So we can solve a system of equations using information that we have from our sequence. Notice that the first term of our sequence is -2. So if we plug 1, as in the first term, into this equation, we better get out -2. So we're looking for a, b, and c that has this property. We also want our a, b, and c to have the property that if you plug in 2 for the second term, you get out 0, which is our second term, and that if you plug in 3 for our third term, you get out 4, our fourth term. So we can build out a system of equations that has however many equations we need. This happens to be a quadratic, so there were 3 unknowns, so we needed 3 equations to be able to determine these. This could have been a delta k for any k constant sequence. Let's say it was delta 4 constant. That means we need a degree 4 polynomial. We'll end up needing a total of 5 constants. So we better have at least 5 entries in our sequence that we can use to create this system of equations. One trick when we're going about solving these, however, is that it actually sometimes helps to think about what the 0th term is. So going backwards, sort of reverse engineering a previous term, can make our lives a little bit easier. In this case, following our pattern, the difference between a 0th and the first term should have been, well, 0. So this 0th term would have been -2. And this just makes our lives a little bit easier when we're going about actually solving this system of equations. If n is 0, a lot of these terms drop out. If we're doing this computation by hand, it's a little bit easier. That said, the main takeaway of all of this is that this is really a generalization of what happens with arithmetic sequences. Arithmetic sequences are the delta constant sequences. They're the sequences that differ by a fixed amount. This is sort of a broader class where we're considering sequences that may not differ by a fixed amount, but whose differences differ by a fixed amount, or whose differences differ by a difference that's a fixed amount, etc. Right? So this whole collection of delta k constant sequences really is a generalization. It's a bigger class than just arithmetic sequences. And these, as it turns out, end up as being our polynomials. So they're actually not too terribly difficult to work with. I said in the beginning that there are some sequences that aren't easy to go from the sequence to a closed form, or even from the recursive definition to the closed form. And the generalization of some geometric series falls into that category to some degree. So there are certain cases of generalizations of geometric sequences for which it certainly is doable, and we're going to talk about that now. But that said, there also are geometric sequences that either just get really messy or really aren't really worth doing in this way. Remember, geometric sequences are those where to get from one entry to the next entry, we multiply by some fixed amounts. So this is one of the simpler geometric sequences. The rule to get from one term to the next term is that we want to multiply by 2. So you may actually just recognize this sequence as the 2 to the n sequence. Really because it's sort of in this simplest form, maybe these numbers just feel familiar. But let's pretend that we don't recognize this right off the bat. Instead, let's work with the recursive definition. Maybe we do recognize that, hey, our first term is 2, and that the rule is that the subsequent term, the next term, is always 2 times the current term. To go from this recursive definition to a closed form, one thing that we can do is telescoping. So let's take our 5th term. So we want to have a general formula for an. Well, let's first try to do a concrete example. Let's try to do a5. Well, I know that a5 is equal to twice a4. All right, cool, progress. But I happen to know that a4 is equal to twice a3, etc. So I can transform our starting sequence, or our starting expression, into, I can simplify it down, I can telescope it to get it into something that we actually know, like a1. So by plugging that in, I can recognize that a5, our 5th term, similarly, I could make this a little bit more general by, rather than doing a5, doing something more general like an, and substituting generic language for this to be able to determine that, in fact, an is equal to 2. Okay. So this technique works. It really shines when we've got a reasonably straightforward equation here. If we've got something like an plus 1 equals 2 times an plus 3, that's certainly something that this can do. Yes, our formula might get a little bit messy, but this telescoping approach can work. So while this is a generalization of a geometric sequence, the sequence that we get from this isn't actually geometric, but it feels similar, it has similar properties, there are other ways of generalizing geometric sequences. Another way of generalizing these geometric sequences is we can say, all right, what if our subsequent entry isn't just some constant times a previous entry? What if we also brought in an even earlier entry? So this should be reminiscent of the Fibonacci sequence, only rather than it being an plus an minus 1, we have some other coefficients in front of these things. So we could try doing some sort of telescoping-like idea if I wanted to turn this into the general equation for, or the closed form for a sequence that was generated by something like this. The problem is that each step along the way, I've got multiple entries in it. So if I started with, let's say, a sub 5, then I'm going to have an a sub 4 and an a sub 3, and then the a sub 4 is going to have an a sub 3 and an a sub 2. Meanwhile, at the same time, the a sub 3 has an a sub 2 and a sub 1. You can see how this sort of branching is just going to make our lives difficult. So as it turns out, this particular type of generalization of a geometric sequence has a reasonably accessible way of transforming a recursive definition into a closed form definition. So this procedure really only works for second order because there are 2 terms, we're looking at the 2 previous terms, linear because there aren't any coefficients, and homogeneous because we're not talking about any constant term tacked on, so fairly narrow scope, but anything that looks something like this, where maybe we have different coefficients, can be solved using this technique. First, I'm going to walk through the general procedure, the general steps for how to find the closed form for one of these sequences, and then we'll talk briefly about why this works the way it does. Okay. So, bear with me here. The first step is that we're going to take our recurrence relation formula, so the rule that says that our n plus 1th term is something depending on the 2 previous terms, and we are going to find what's called the characteristic polynomial. In other words, depending on what our constants r and s are, we plug them into this polynomial. So in our example here, the characteristic polynomial would be x squared minus 5x plus 6. Once I have this characteristic polynomial, I want to find its roots. In other words, I want to know what values of x can I plug in to make this polynomial equal to 0. So this is going to depend on r and s, but this is just an equation that I can solve, and whatever I get out, whatever my 2 answers are, x1 and x2, these are the roots of this polynomial. So the point of bringing this up is to find these two values x1 and x2 because they're going to have some special property relative to this recurrence relation. Next, I want to look at these two values x1 and x2. If they're different, then my closed form version, my an, is just equal to some constant times one root to the n plus another constant times the second root to the n. If they are the same, in other words, if when I solve this, when I find the roots of this polynomial, I get two things that are actually the same, then the general form for this closed form ends up looking a little bit different. We have this extra n term. But regardless, what this is saying is that whatever this root is going to dictate the idea that, hey, the closed form is going to be something of the form x1 to the n. All right, so that was a lot of what I don't like about math education, which is, hey, here are all the steps, and then let's learn the steps. But bear with me, we're going to work through an example and then discuss a little bit why exactly this seemingly random procedure is going to tell us something about the closed form of a recurrence relation. Okay, so working through an example, let's say we have our recursively defined sequence where the next term is 5 times the previous term minus 6 times the term before that. Okay. Since we're referring to two terms, we need to specify not only our first case, but our first two cases. Okay, so those of you in comp sci have maybe even been a little bit annoyed that I, in the past, have referred to the first term as term 1 and the second term as term 2. There are a lot of good reasons to not do it that way, to instead say that our first term is our 0th term, and then have our second term be our first term. So what we're really just doing is saying that if we've got a list of numbers, we're going to start counting with 0. And if you've never had any comp sci, that's going to seem weird, but in both comp sci and in the math that we're doing here, it's going to make our lives a lot easier with some calculations. Early on, when I was saying solve a system of equations, it helps to have a 0th term. That type of thing is going to keep cropping up. So we might as well pick up the habit of, when convenient, calling our first term our 0th term. It is important to bear in mind that we need to make sure that we're clear that we're doing this. Anyway, if our 0th term is -3 and our first term is -2, then we want to come up with some closed form expression. We want to know what the nth term is without having to go through this recursive procedure. Okay, a way that we can find that, because this is a second order homogeneous linear sequence, we can use this procedure. So we want to know the characteristic polynomial, we want to find its roots, and then plug it into something that looks like this. Well, the characteristic polynomial just comes from these terms. This is r and this is s. So the polynomial in question is x squared minus 5x plus 6. So that's our characteristic polynomial. We want to know its roots, so we want to set it equal to 0. This one is particularly easy in that we can factor it. If you can't factor it, you have to use the quadratic formula. This one just factors as x minus 2 times x minus 3. So the roots of this equation are 2 and 3, meaning that these are the numbers, 2 and 3, that plug into this form. So the closed form expression that we're looking for looks like this. Well, because 2 and 3 are different. So in other words, we're looking for something that looks like a constant times 2 to the n plus some other constant times 3 to the n. In other words, the recurrence part is going to come from some combination of these exponentials. I said before, this is a generalization of a geometric sequence. Geometric sequences are the ones that look like this. All right. So we've said that our closed form looks like this, but we still need to solve for these coefficients. Earlier in this video, we were solving for a, b, and c. Now we're solving for c1, c2. Different notation, same idea. We want to know what constants get plugged in here to make it so that our 0th term is -3 and our first term is -2. So we want our 0th term to be -3. So if I plug in 0 in for n, I hope to get out -3. If I plug in 1 in for n, I hope to get out -2. Cool. So now I've got two equations and two unknowns, c1 and c2. I can solve the system of equations for c1 and c2. If I do that, and I'm not going to go through the details of that, I believe that c1 ends up being -7, c2 ends up being 4. In other words, this is saying that the answer, the closed form expression for this recursive sequence is -7 times 2 to the n plus 4 times 3 to the n. Okay, so this may have felt like we're just following steps, and to some degree that is what we're doing. I want to talk very briefly about why this does what it does, but if you're interested in more details, I highly encourage that you read Theorem 5.3.1 in the book, which proves this statement, that the roots of this, or that this procedure results in closed forms expressions for our given recurrence relations. All right. The general idea is that this characteristic polynomial is reflective of this sequence itself. So early on, when I was talking about telescoping, I mentioned that if we have a sequence that has these two terms like this, and if we try to do a telescoping approach, we're going to keep getting larger and larger expressions, because each time we're going to replace a term with two other terms, and it's going to sort of develop that way. Well, this characteristic polynomial is reflecting that. When we set this thing equal to 0, this is equivalent to saying that x squared equals rx plus s. In other words, this form is reflecting this effect. And by finding the roots of this equation, we're finding the pieces of it that don't change. In other words, the roots of this equation being, in our example, 2 or 3, is saying that things like 2 to the n aren't going to change under this effect. Okay, that was a very, very hand-wavy explanation. I really do encourage you to read through the proof in the book. I'm not going to go through it in class, but it's especially good to read a slightly more advanced proof than the ones that we're writing. So highly recommend.